so there's my generator, there's my load. Gee, that looks just like we're starting with, doesn't it? Just an ordinary voltage source and a resistor. Okay, it is, but if you have a battery or generator or something, it's got some kind of internal resistance in it. Why? Because, there's a chemistry inside the battery, and when the current flows through it, there's some impedance from the makeup of that electrolyte inside the battery and the interaction with the poles. Or if you had an AC generator, it's got windings made of metal. They're usually copper. They have resistance. And you want to get something called power to show up in the load. Now here's a couple of interesting thoughts. If this thing really has its own internal impedance, I'll draw a dotted line here. That's the resistance, I call it R sub I, internal resistance, R sub L, load resistance. If you happen to have some internal impedance here, you got the element of a voltage divider. One of these things where you have two resistors in series. One belongs to the generator, one belongs to the load. The internal one and the external one. If this one is much higher than this, the voltage will drop across here and not so much here. And this bringing up of this resistance will reduce the overall current because Ohm's law still applies. Whatever voltage drop you get is going to be the current through the device times the resistance. Okay, well, what if this were big and this were small? Same problem in reverse. Now all your power, which is the sum of that current and that voltage, is going to be affected because when you bring the resistance up, you're going to bring the current down. That's not good. And if you bring the resistance of one part of the circuit up relative to the other, it's going to see the voltage drop at the same current. Remember, they're in series, so they both have the same current, which means he's going to get more of the power than he does. So what do you do to get the most power from your generator to your load? The rules are two. It took a little calculus in a course that studied the subject called linear network theory that I took in college. And we figured out by doing a little calculus, solving for the peak value of the second derivative. And here's the answer. If you have some kind of reactance here, and some kind of reactance here, and resistance on both sides, and here's your generator, called a radio transmitter, here's your load, your antenna. To get the maximum power to go from the generator to the load, your generator's internal impedance has to be equal to the load impedance. Your generator's internal resistance has to be equal to your load's resistance. Remember, if the resistance is higher on one than the other, it gets the voltage, it gets the power, but it also by going higher, it brings down the current. So basically, you lose one way or the other. The best deal is to make them equal. And the other one is L and C. Your reactances have to be equal and opposite. If you happen to have your voltage leading, you're going to have less power because you have a power factor that we talked about, a shift in phase. You don't have the coincidence of the current and the voltage happening at the same point in the cycle. You want to pull those together. So what you want to do is you want to do what this high school experiment did, where you have the capacitor, the resistance from the form of a light bulb, and the inductance. You want these guys to be equal to each other in impedance, so they cancel each other out. You want your transmitter's reactance canceled out by your antenna's reactance, or more appropriately, your antenna's reactance is going to be determined first, and you want to do something on the transmitter side to adjust for it. If your antenna is too short, it's going to look like a capacitor. The only way to easily understand that is you're going to have a traveling wave instead of a standing wave. It's going to be more like this. And it's going to, if it's too short, have the current leading the voltage. And that's going to be characteristically what a capacitor does. So what you want to do is offset it by putting an inductor there to do exactly what this guy did to offset this guy. Equal resistance, equal and opposite reactance. If your load is capacitive, if your antenna is too short and looks like a capacitor, put an inductor in series with it and it will do exactly what this circuit did. It will cancel out that reactance and give you full power to the load. And that's what a matchbox does. In ham radio, you have your transmitter, you have your antenna, and very often in between you have a box that has either resistance, I should say either inductance or capacitance. It usually has resistance too. If you look at your matchboxes, they usually say reactance, resistance on the two knobs that you have to fiddle with. And what you do is you compensate so that your load will have equal resistance and equal and opposite reactance to what the transmitter has, or actually the other way around, the transmitter will compensate for the antenna's imbalance relative to the transmitter by adding inductance in the form of a capacitor or inductor, depending whether it's too long or too short, and resistance. And that, by the way, is how a lot of antennas operate these days. They're not cut for a particular frequency. You got a backyard that's X number of feet long, you just run a piece of wire there. And you feed it in the center, or you can even feed it on the end. And round the other end, making it like a quarter wave radiating element instead of the half wave that you would prefer it to be. Works just fine. I won't say as well as a dipole will, but it does work. And what you do to make up for the incorrect length is you have this matchbox and you add in the reactances that aren't there that have to be there to match what the transmitter's doing or compensate what the antenna's doing incorrectly. And all of a sudden your transmitter says, hey, I've got a perfect load. A perfect load is a resistor. No reactance. Remember, the reactances have to be equal and opposite. The resistances should be equal. The best deal is it looks like a resistor. Good time to bring up one other little thing. When you buy coax cable, there's a resistance value or impedance value that comes with it. I want 50 ohm coax. If it's for cable TV, you want 75 ohm coax. When we had this twin line stuff, it was called 300 ohm coax. I guarantee if you put a voltmeter, or more appropriately an ohm meter, on that cable, it isn't going to be 300 or 75 or 50. It's not going to be anywhere near it. It's going to be infinite. Why? Because it's an open circuit. You got two wires going parallel to each other. Nothing's connected to the other end. Or if they're tied together at the other end, it's going to be dead short and it's going to be zero resistance, 0 ohms. Maybe a few ohms because of the copper wire in the middle. So what in the world are they talking about when they talk about 50 ohm coax cable? It has nothing to do with intrinsic resistance. I can guarantee that. What it is what's called characteristic impedance. I'll explain that. This stuff isn't just for radio buffs like us, it's for computer guys too. You'll deal with it when you're setting up things like Cat5 cable for Ethernet or whatever. Here's your generator, alternating current, radio frequencies. Here's your transmission line. And if this stuff is 50 ohm coax, what that really means is if resistor at the end of it that happens to be 50 ohms, what comes out of here is going to have nothing reflecting back. In other words, the spacing between the conductors, the material in between those conductors to keep them apart, you know, remember the coax cable, you got this braided thing on the outside, and you got the cable in between. What's filling the space in between is some plastic material, polymer. It's called a dielectric. Dielectric, just like the dielectric between the plates of a capacitor, it means something that does not conduct electricity. And it's part of the equation that determines what is the characteristic impedance. The idea is this, like the string I attached to the doorknob. I snapped a line and away went down the line until it hit something that wasn't a piece of string, it was a doorknob. The doorknob didn't bounce up and down like the string did. It was a discontinuous part of the transmission path of that wave. And when it saw that solid surface, there was a reflection back. Now, this is why radar works, isn't it? Here's my radar dish, and it's putting out radio signals. And here's some airplane out here, the bad guys. The radio signal hits this, and there is a reflection. Why is there a reflection? Because when you're sending a radio signal out in the air is conducting it. The air has a characteristic impedance of its own. It actually does. It's the ratio between what the electrical and what the magnetic vectors of the electromagnetic wave are. That's the electrical wave, that's the magnetic wave. They're always at right angles to each other, always 90 degrees out of phase. Excuse me, 180 degrees out of phase. And they happen, in the case of free space, happen to be 377 ohms. Just an interesting number to know. Not that it's ever going to be in the test, but it's what we learned when we studied microwaves and radar. Determined it to be. All right, so comes this airplane, and this airplane ain't 377 ohms. The wave hits it and says, uh-oh, discontinuity, there's going to be a reflection. You have a transmission coefficient, you have a reflection coefficient. The wave hits the surface, it's not the same impedance as what it's been going through. Some of that energy is going to be bounced back. And of course, the antenna is ready to receive it because it sends out a pulse and waits for an echo. The timing of that pulse tells it how far it is. You get about 25, for every mile it takes about 25 nanoseconds. Microseconds for that signal to make the round trip. If you do the math, speed of light, distance, and all that. So how far you are determines the timing of the echo, and of course which direction the antenna is pointed when it sees that airplane tells it the direction. So radar is radio detection, meaning finding an echo, and ranging, how far is it, which direction. Range and bearing, just like that polar coordinate thing. You got a certain bearing angle and you have a certain range, or distance from the center. That's what you're trying to do with radar. That's what you're trying to do with your transmission line on your radio. You're trying to get the discontinuities to not be there. If you have a sloppy connection, like a bad connector on the coax cable, you're going to get reflection. If you have that ring around this piece of twin line, you got the reflection of the discontinuity in the transmission line, which is why we got away from twin line. When we got bigger screens and sharper pictures and all the imperfections really started to make themselves felt, especially when you went to color, you could really see the detail. Just like you can see the puck in a hockey game more easily in color than in black and white. All those reasons fit together. So that's the whole idea about waves, matching, and so on. Well, go ahead, good timing.
Alright, and I'm sorry, I'm the only person asking questions, so.
No,
if
please.
I'm being annoying, just tell me.
Bring it on, I need more.
Okay.
I need
So,
10 more like you.
half more wavelength, or half a wavelength.
Mm-hmm. Is a
Quarter wave, which is your ground.
which is a half
plane, so you got
wavelength,
the
but it's
half,
split
right?
between the counterpoise and the actual radiating
Wi-Fi
element.
base.
That is
So-
Okay, there's a reason for that. That's actually 2 quarter wave elements stacked. When you have these 5/8 wave elements here on a car, there's a coil in the middle. You will note, there's a low. And what they've done is, they've had 2 elements, basically, they took the quarter wave and they split it up. And why 5/8 works, I'm not sure, but because it is what it is, this coil is actually adjusting for the shorter part, the shortening of it. There's also a coil down here that does the same thing. And the reason they make it 5/8 is what they're trying to do is change a wave that looks like that into a wave that looks more like a donut. They're trying to flatten the wave. So you got an element on top and an element on the bottom. They add together in such a way that you get a flatter pattern. The idea is, why send energy up or energy down when you really are talking to people in the same plane where you are? So the antenna produces a change of the shape of the wave to more of a donut. And that is a great segue, because it's the very next thing I was going to get to, which is, why do we have all these funny looking antennas so different from each other when I just explained that a basic antenna is just a dipole? Well, one word, gain. Consider this, the headlight on your car, if you were to actually take it and put an ammeter on it, measure the current that flows through it, is, I've done this so I know, about 5 amps. Standard headlight of the car will draw about 5 amps. And the voltage is obviously 12 volts, so 5 amps, 12 volts. What kind of power is that light bulb radiating? How many watts? 60, of course. So it's a 60-watt light bulb. But if you look into the headlight of a car, it just looks a heck of a lot brighter than 60